In the last few lectures, we examined some problems of unidirectional transport. Okay. Both of which were involved similarity transforms. Okay. The first one was diffusion from a surface into an infinite film in the z direction, where the T was equal to T infinity far from the surface, and the temperature was increased to T naught at the surface, at T is equal to 0. Okay. And we had got the scale temperature T star is equal to T minus T infinity by T naught minus T infinity. Okay. In terms of a similarity variable, that was 1 minus error function of psi by 2, where psi is a similarity variable z by root dt, dimensionless, and in fact the only dimensionless parameter that you can make from z and t. Okay. And this we got by solving the equation partial t by partial t is equal to alpha d square t by dz square. Okay. The second was injection of a pulse, decay of a pulse into an infinite medium. Okay. Where a pulse of mass m per unit area is injected at time t is equal to 0, and then that spreads into the medium due to diffusion. And for that also we had got a similarity solution in terms of the same similarity parameter, as C is equal to m by 2 root pi dt e power minus z square by 4 dt. Okay, that was the second solution that we had. Okay. Now we will consider the diffusion into a finite domain, where we will once again use the similarity transform, but in this case there is a finite length scale. Okay. There is a finite length scale in the problem, a time dependent length scale. Okay. So the problem is as follows. Okay. We have this is a solid block, let us say of metal, let us say solid, which is getting heated because there is, so this is at its melting temperature Tm, this solid is at its melting temperature Tm, and I have above that a liquid pool. Okay. So at this surface T is equal to Tm, and at this surface T is equal to T naught, which is greater than Tm. Okay. So because of the gradient in temperature, T naught is greater than Tm, because of the temperature gradient T naught is greater than Tm, there is a heat flux coming downwards, and that heat flux melts the solid. So the solid has thermal conductivity rho, Cp is the specific heat, lambda is the latent heat, the heat required for melting per unit mass of the solid. And we will assume for simplicity that rho and Cp are the same in the liquid and the solid. So that is So how do I solve this problem? This has a height h, this liquid film has a height h above the solid, and as the solid melts, this height h is increasing. So the height h is a function of time. Okay, it is increasing as a function of time. Okay. The temperature, scale temperature can be defined for this configuration as T star is equal to T minus Tm by T naught minus Tm, okay, which means that at the surface, top surface, T star is equal to 1, okay, and at the bottom surface, T star is equal to 0, because temperature is just the melting temperature, okay, because the temperature is just the melting temperature. Okay. And I will define a scaled z, z star is equal to z by h of t, where h is the height, which is a function of time. Okay. And I want to know for what systems can you get a similarity solution, okay, for this particular problem, where the temperature field depends only upon z star and not individually on z and t. Okay. H itself is a height, which is a function of time. So, the boundary itself is a function of time. So, the temperature equation, okay, is equal to alpha d square T star by partial z square. Okay. Once again, I have to represent this in terms of the scaled variable or the similarity variable z star. Okay. So, partial T star by partial z is equal to partial z star by partial z, partial T by partial z star. Okay. Differentiation using chain rule, d square t by dz square. In a similar manner, I will get this as 1 over h square d square t by dz star square. Note that h in this case is a function of time. Okay. In this particular case, h is a function of time. Okay. Partial t by partial t, okay, the derivative with respect to time, is equal to partial z star by partial t dt by dz star. Okay. Z star is equal to z by h of t. Z star is equal to z by h of t. Therefore, this will be equal to minus z by h square dh by dt dt star by dz star. Okay. And I can write this therefore as z by h is z star. So, z star by h dh by dt dt star by dz star. Okay. So, substituting this and this into the conservation equation, okay, I will get minus z star by h dh by dt, okay, dt star by dz star is equal to alpha by h square d square t star by dz star square. Okay. Multiply throughout by h square by alpha. So, I get coefficient 1 on the right side, okay, and I will get here d square t star by dz star square is equal to minus h by alpha dh by dt, okay, times z star dt by dz star. Okay. So, I can get a similarity solution only if this term here is a constant. Okay. I can get a similarity solution only if this term here is a constant. Okay. So, I need to know what is dH by dt. Okay. So, this term here, okay, minus h by alpha dH by dt. Okay. Okay. This is equal to minus half 1 by 2 alpha d of h square by dt. Okay. Okay, you can write it either way, but if you look at this term, okay, this is like a velocity. Okay, this is like a velocity of the interface. H is the length scale, is the characteristic length of that material that is molten, and alpha is the diffusion coefficient. So, this is similar to a Peclet number based upon the velocity of the interface. Okay, this is like a Peclet number based upon the velocity of the interface. Okay. Okay. So, I had got the conservation equation here. I also have another condition that has to be satisfied. So, I had applied boundary conditions T star is equal to 1 at z is equal to 0 and T star is equal to 0 at z star is equal to 1. Okay. So, this I will call as z is equal to 0, this is z is equal to h. Okay. I am taking z in this direction, z is in this direction. Okay. So, the temperature is 1 at z is equal to 0 and 0 at z is equal to h, or z star equals 1. But there is one additional condition that has to be satisfied here, okay, and that is the heat that is transferred in a time delta t has to be equal to the latent heat times the mass of material that is molten. Okay. So, let us assume that this interface goes down by a small distance delta h. Okay. If this interface goes down by a small distance delta h within a time delta t, okay, if the interface goes down by a small distance delta h within the time delta t, okay, then the heat flux, okay, the total heat transferred is a heat flux times the area times delta t, because heat flux is equal to heat transported per unit area per unit time. Okay. So, the total heat transferred in time delta t is equal to qz into the area into delta t. Okay. Okay. So, if the interface goes down by a distance delta h in a time delta t, total heat transferred is qz A into delta t. Okay. Volume of molten material in a time delta t is going to be equal to delta h times A. That is the volume that is melted in this time delta t. Okay. Therefore, the mass of molten material is equal to rho A delta H, okay, and therefore, the total amount of heat that has to be transferred, okay, heat transferred is equal to rho A delta H into the latent heat per unit mass that is required for melting a material. Okay. So, that is the heat, the latent heat that is transferred. Okay. Therefore, the heat that is transferred has to be equal to the latent heat of the material times the mass of material molten, okay, or qz A delta t is equal to rho A delta H times lambda. Okay. This delta t should be a time, not temperature. Okay. And therefore, I will get delta H by delta t is equal to qz by rho lambda. Okay. This qz is at the location z is equal to h. Okay. And this is equal to, I can use the Fourier's law of conduction, minus k by rho lambda dt by partial t by partial z at z is equal to h. Okay. Written in terms of the scaled variables, this can be written as minus k by rho lambda t naught minus T m by h dt star by dz star at z star equals 1. Okay. And the left side, in the limit as delta t goes to 0, this becomes dh by dt. Okay. This becomes dh by dt. Okay. Okay, if I take the h to the left side, I will get h dh by dt is equal to minus k by rho lambda t naught minus T m into dt star by dz star at z star is equal to 1. Okay. And note that I had defined this p as h by alpha dh by dt. Okay. And I said that this has to be a constant. This has to be a constant if we are to get a similarity solution. Okay. This has to be a constant if we are to get a similarity solution. Okay. So, I can divide this throughout by alpha. Okay. H by alpha dh by dt is equal to minus k by rho lambda into alpha here, okay, and dividing left and right sides by alpha. Okay. This factor k by rho alpha is equal to k by rho into Cp, okay, sorry, alpha is k by rho Cp. Okay. Okay. The thermal diffusivity is the conductivity divided by rho Cp. Okay. Okay. So, this is just equal to Cp, okay, the specific heat. Yeah. Therefore, I get h by alpha dh by dt is equal to minus, okay, Cp into T naught minus Tm by lambda dt star by dz star at z star is equal to 1. Okay. This is the same as the parameter p that I had earlier. Okay. This is the same as this parameter here, okay, which I said has to be a constant. This energy balance condition, that the total heat transferred within a time delta t has to be equal to the latent heat times the mass that is molten. Okay. That shows us that this is in fact a constant. Okay. H dh by dt is in fact a constant, because once I express temperature in terms of z star, then the temperature gradient at z star is equal to 1 has to be a constant. Okay. Okay. This number, okay, this goes by the name of the Jacob number. Specific heat times temperature difference divided by latent heat. Specific heat is energy per unit mass per unit temperature multiplied by temperature difference divided by latent heat, energy per unit mass. Okay. So, this is a dimensionless number. The ratio of the specific heat times temperature difference, that is what is called the sensible heat, and the latent heat. Okay. This is equal to P, which is equal to h by alpha dh by dt. Okay. I should note that this dt by dz is actually a negative number. Okay. dt by dz is actually a negative number, as you can see from here. Okay. You can see it from here. The temperature decreases as z increases. So, dt by dz has to be negative. Okay. Therefore, this parameter p has to be positive. Okay. Therefore, this parameter p has to be positive and dh by dt has to be positive. The height increases with time. Okay. So, that is okay. So, now we still have not solved the problem. We have to solve this equation. Okay. We have to solve this equation where this is the parameter p, okay, the Peclet number. Okay, this is the Peclet number. Minus p z star dt star by dz star is equal to d square t star by dz star square. Okay, note that we still do not know what is the parameter p. Okay. This J A is a material parameter. It only contains the temperature difference, the sensible heat and the specific heat and the latent heat. But we still do not know what is this parameter P. Okay. That we will determine from the boundary conditions. Okay. That T star is equal to 1 at 1 and 0 at 0. Okay. So, this solution, if you recall, we had earlier solved the equation for transport into an infinite medium. Okay. Minus psi by 2 dt star by d psi is equal to d square t star by d psi square. Okay. The temperature we had got was T star is equal to C1 error function of psi by 2 plus C2. Okay. The solution we had got is C1 error function of psi by 2 plus C2. Okay. This can be solved in a similar manner, except that I have to now scale z star by p. Okay. So, this parameter p has to be used for scaling z star. Okay. And once I do that, right, if I scale this, if I define the equation as minus p, minus z star dt star by dz star is equal to 1 by p d square t star by dz star square. Okay. And I define a new variable as p power half times z star. Okay. Then you can see that you reduce to this equation, except this factor of 2 is not there. Okay. So, by doing this manipulation and defining z plus is equal to root p times z star. Okay. If I define z plus is equal to root p times z star, I get minus z plus dt star by dz plus is equal to d square t star by dz plus square. Okay. Okay, so I can solve this equation. And finally, the solution that you get is that T star is equal to C1 error function of root of p z star square by 2 plus C2. Okay. C1 error function of root of p z star square plus C2. Okay. And then you apply the boundary condition T star is equal to 1 at z star is equal to 0 and T star is equal to 0 at z star is equal to 1. Okay. And you get the final condition T star is equal to 1 minus error function of root of p z star square by 2 by error function of root of p by 2. Okay. So, that is the final solution, okay, for the temperature field. We are not done yet, because we still do not know what is P, right. We have to solve the rate of change of height as a part of the problem, part of the solution. Okay. To do that, we have to get what is the heat flux. Okay. So, the heat flux or the scaled heat flux dt by dz at is equal to root of, okay, I can just differentiate this with respect to z and set z equal to 1 root of 2 pi 2p by pi, okay, into e power minus p by 2 by error function of root of p by 2. Okay. Just differentiating this to get the error function and then substituting Okay. So, you recall this equation that I had, okay, for the temperature field. Okay. You recall this equation that I had for the temperature, for the boundary condition for the temperature, that is h by alpha dH by dt is minus Jacob number into P. Okay. Okay. So, P is equal to Jacob number into dt by dz at z equals 1. Okay. That was the condition that whatever heat is transferred should be equal to the mass of material molten times the latent heat. Okay. So, in that I substitute this expression for dt by d star, and I will get P is equal to minus the, I am sorry, this should be a negative sign because the temperature has to decrease. Okay. So, I will get plus the Jacob number into root of 2p by pi e power minus p by 2 by error function of root of p by 2. Okay. So, this implicit equation has to be solved to determine what is P, or the rate at which the surface is melting. Okay. This implicit equation, which was obtained by substituting the expression for dt by dz at z is equal to 1 into the energy balance condition at the interface, that whatever heat is transferred has to be equal to the amount of material that is molten, the mass times the latent heat. Okay. Jacob number is something we know. Okay. Ja is equal to Cp times T naught minus Tm by lambda. Cp and lambda are material properties. T naught minus Tm, melting temperature is a material property. T naught is the temperature that you fix for the top surface. Okay. So, this equation has to be solved implicitly, knowing what is the Jacob number to determine what is P. Okay. This has to be solved implicitly, knowing what is the Jacob number to determine what is P. Okay. This is an implicit equation, it cannot be solved directly. However, we can get the solution in limiting cases. Okay. We can get the solution in limiting cases for Jacob number small compared to 1. Okay. For Jacob number small compared to 1, you would expect P also to be small compared to 1. So, you can use an expansion, this kind of an expansion of this parameter in the small parameter P. Okay. And then solve it to get P is equal to Ja minus Ja cubed by 3. Okay. So, this is our, okay, for P much greater than 1. Okay. For P much greater than 1, error function goes to 1. I told you that the error function of x goes to 1 as x goes to plus or minus infinity. Okay. So, the error function goes to 1, and I will get an expression for the Jacob number as Ja is equal to root of p pi by 2 into e power p by 2. Okay. So, these are the relations in the limit as p goes to 0 and p becomes large. Okay. And this relationship I can plot as a function of the, as a relation between Jacob number and the Peclet number. Okay. So, if I plot Jacob number versus p, okay, I get something that is linear initially and then it tapers off, okay, as Jacob number increases. So, given a Jacob number, I can determine what is P. Okay. So, if I given a Jacob number, from this relation I can determine what is P. Okay. And I know that P is equal to h by alpha dH by dt. That is a constant. Okay. It is independent of time. Okay. So, therefore, I can determine what is dH by dt. Okay. So, therefore, dH by dt is equal to alpha by h into p. Okay. Or alternatively, half d of h square by dt is equal to alpha times p. Okay. If h is equal to 0 at t is equal to 0, then I will get h square is equal to 2 alpha p t, just by integrating this equation directly. Therefore, the height increases proportional to time. Okay. The height increases proportional to, I am sorry, the height increases proportional to square root of time, h is equal to root of 2 alpha p t, okay, where p is a constant and p, which is an implicit function, is related to the Jacob number by this graph that I have shown here. Okay. So, this is another application of the similarity solution for this particular case, where I have a height that is dependent on time, okay, but I still can get a similarity solution in this case because of the energy balance condition at the interface, okay, because the energy balance condition at the interface is such that I can still get I require this be a constant in order to get a similarity solution, and from the energy balance condition I find that this is actually a constant if t is only a function of z star. Okay. Okay. So, both of those are consistent, and therefore, I was able to get a similarity solution in this case. So, these are solutions, the similarity solutions for heat transfer and for mass transfer. I will discuss one further example, that is into a cylindrical coordinate system, in the next lecture, and then we will go on to discussing transport into a finite domain. Okay. So, that will be the next series of lectures, transport into a finite domain. So, I will first discuss similarity solution for heat transfer in a cylindrical coordinate system before we go on to transport into a finite domain. I will continue this in the next lecture. I will see you then.